Whenever we have a new operation in mathematics, we tend to take a moment and talk about what kind of properties this operation might have. So let's do that here for the cross product. And to make things easier, let's talk about some general vectors like the vector u, the vector v, the vector w. And if we wanted to super generalize it, we could assign each of these vectors components, but we don't really need to go that far here. We're also going to pick c to be a scalar. Remember, scalars are non-vector quantities, like just regular numbers. One of the first properties is the anti-commutative property, and we talked about that in the last video, that anti-commutative means you can change the order of the objects in the operation, but in order for that to stay equal, we would need to multiply by a negative. We also have a distributive property. Distributive property says that if you are doing a cross product over addition, so I'm crossing the vector u with the sum of two vectors, v and w, then I can essentially distribute the cross product operation so that I'm doing two cross products and then adding them together. Multiplication by a constant is another property. That's saying if I'm calculating a cross product and then multiplying it by a constant, I could actually multiply that constant to any one of the vectors individually. And this is useful because calculating a cross product, as we'll see later, is a little bit tedious. So if you have a constant multiplied to one of your vectors, you could factor it out, calculate the cross product between the two vectors like you have on the left over here, and then multiply the constant back in. And it doesn't matter if that constant were on the first vector or if it were on the second vector. You could factor it all the way out of the outside of the two vectors and the cross product. We also have a property that says that when you cross a vector with the zero vector, that the result is the zero vector. Now, let's pause for a second. This is a vector here, not the number 0. And it's important to talk about this because remember that we're interpreting the cross product as a vector that's orthogonal to the other two vectors. So everything by definition, or nothing by definition, could be perpendicular to that 0 vector because it doesn't have one direction. It could be infinitely different directions, and it has no magnitude. So when we talk about making a perpendicular vector to the 0 vector, that gets a little weird. So we're going to define this to say that it's the 0 vector. When you cross u with the 0 vector, you get a 0 vector. Again, not a scalar, that's a vector. Next, we have crossing a vector with itself. So if I take the vector v and I cross it with itself, I get 0. And we talked about that briefly in the right-hand rule example of the last video. We'll do some worked out examples of this where you see that that is the only option that you could have. Crossing a vector with itself will result in a 0 vector. And then lastly, we have something called a scalar triple product. And this is pretty cool. It's a triple product because there's 3 vectors. It's a scalar triple product because the result is a scalar. Remember that game, scalar or vector? Well, u is a vector, v is a vector, w is a vector. When we cross v with w, we get a vector. So then that means this little dot between u and the parentheses, that's the dot product because we have a vector to the left and a vector to the right. And when you dot two vectors together, you get a scalar. So that's our scalar triple product, which we'll see some more of that in a few minutes. Almost forgot that we were going to use these properties to simplify this expression on the screen. All right. So we have 2i crossed with 3j, and then we're going to cross that with the j vector. So looking at our properties, we want to see what we can apply here. How about we start with the constant multiple rule? I have a cross product, and the vectors in my cross product have coefficients or constant multiples, however you want to look at it. So let's factor each one of those out. I could write 2i hat crossed with 3j hat, which is then crossed with j hat. But I could also factor out the 3, so 2 times 3 times the cross product of I crossed with j, crossed with j again. Or we could write that as 6i hat cross j hat cross j. I hat crossed with j hat, we actually did that earlier with the right hand rule, so if you forgot, go ahead and use your right hand to find out that I crossed with j is the k hat vector. I'll bring down that 6 multiplier and then bring down the cross j hat. And then k crossed with j in that order. Again, using that right hand rule, we'll find that this is the negative I hat vector. And we need to bring down our 6 multiplier. So our final answer is negative 6 I hat.